Moving on to the Adept level for solving right triangles. This little diagram up here, again I have a horizontal, but this line going diagonally downward, we can call this angle here the angle of depression, just because it's going down. Just some terminology in case you see this word in a problem. So for this example here, we just want to determine y and z. So that's this height here and the hypotenuse of this triangle here. We can assume that the top and bottom lines are parallel. So I can actually denote that by putting little arrows here. So these two lines are parallel. Okay, so method one, and again because I don't have any room I couldn't construct the slide this way, but in your notes everything I write in this area you should complete down here. So that's 90 degrees, therefore this is 90. So if this piece is 65, we have no choice. This is complementary, so this must be 25 degrees. Perfect. So let's use that angle. Well, opposite to the 25 degree angle is this, which we're given as 5. And the adjacent is y. Opposite, adjacent, we use tangent. So the tangent of 25 degrees is opposite over adjacent. All right, so solving for y, just skipping some of the steps, it's just going to be 5 divided by tan of 25. That's going to be an ugly decimal, but no matter. And we get about 10.72. And there we are. Moving on, let's figure out z. So I'll do that in red. So if I use this angle again, and I use this opposite of 5, well, z is the hypotenuse. So for that I need the sine ratio. So the sine of 25 degrees is the opposite divided by the hypotenuse. And there we go, that's my z. So therefore z is 5 divided by sine of 25. So let's work that out. Now it's the hypotenuse, so I better get a number bigger than 10.72, otherwise we're in trouble. Oh good. 11.83. All right, that's all we're asked to figure out, y and z. There you go. So let's do the same problem again, but let's find a different way. All right, recall that we were told these lines are parallel. Well, when that happens, and I have a diagonal line going across like this, kind of looks like a z, in this case a big backwards z. This being 65 tells us that this angle is also 65 degrees. Okay? So I'm going to use this angle instead. All right, so let's find y. Right? So y is the opposite, 5 is the adjacent, so I can use tan. But I'm using a different angle this time. So the tangent of 65 degrees is the opposite divided by the adjacent. All right, so let's get y by itself just by multiplying both sides by 5. So therefore y is just 5 times the tangent of 65, and we should get the same numbers before. I hope. And lo and behold, we do. Okay. So what remains to be found is z. Well, I'm going to do something much different this time. All right. We could use trigonometry, but because we have a right triangle and I know 2 of the sides, I can use Pythagoras to figure out the missing one. So that's what I'm going to try right now. Remember, a squared plus b squared equals c squared, which means 5 squared plus y squared, which I now know to be 10.72. That's the hypotenuse squared, so this would be z squared. Now, just remember that this number here has been rounded, so when I actually perform my calculation, I'm going to keep more decimals here. I've actually stored this number in my calculator's memory, so I don't have to type it again. So, z squared, I can work out all this. So 5 squared plus 10.72 squared gives me about 139.97. So therefore z is just the square root of that. And I get 11.83. Okay. Now I actually didn't have this number in my calculator's display. I had all the decimals remaining. Let's see what we'd get if we use this rounded value. See how far off we'd be. So square root of 139.97. No, I would still get 11.83, so it works out okay. But clearly you can see we get the same numbers regardless of our method.